ఈ లెటర్ నాకు అర్థం కాదు.
మాట్లాడుతుంది.
హలో హలో
Silence, please.
హలో హలో
సరే సార్ అయింది సార్. ఎస్ సార్. సార్ విజిబుల్ గా ఉంది సార్. నైస్ సార్. ఓకే. Dear participants and the delegates in the one-day international webinar, and our beloved principal and all the faculty members and students and scholars, a hearty welcome to the today one-day international webinar on recent trends in chemical sciences 2022. We have a great speakers with us. Two are from IIT and one is from Ireland. They are from very low background and also they are from our government colleges. One speaker from Government Degree College Chodavaram, another speaker from Government Degree College Guntakallu, and other is also from like a normal degree college. But they are now in a big position like in IIT. So they all are very inspiration to all our fellow students and our faculty members and scholars. So now our beloved principal of the college, Dr.I.VIJAYA will address the participants and delegates and students and scholars. Sir Vijay Babu sir, please start the session, sir.
Hello. Can you hear me, please? Yeah. Ramesh garu, please unmute yourself.
Sir.
Yeah. Can you hear me? Ramesh garu.
Yes, sir.
Yes,
Yeah.
sir.
Okay. Right. Hello, dear participants. I extend warm welcome to this one-day international webinar on recent trends in chemical sciences, RTCS 2022. Really, I would like to congratulate the Department of Chemistry on conducting this wonderful program, international program. This webinar is definitely going to be a yeah, just hold a minute. There is some disturbance. Yes. Let's go ahead. And I also would like to extend warm welcome to all the participants. And today we are fortunate enough to have wonderful speakers from IITs and also from University of Dublin, Ireland. I extend warm welcome to the resource persons Dr. M. Raghavendra, Assistant Professor from IIT-Bhilai, and also Dr. D. Apparao, Assistant Professor from IIT Kanpur. And my warm welcome to Dr. Vadde Ramu, Research Scientist from the University of Dublin, Ireland. And also would like to extend welcome to all the participants around Visakhapatnam and also from other parts of the country. I see a few participants from IITs as well. Really, coming together like this in webinars definitely gives us an experience of exchanging the expertise as well as learning from each other. And this webinar is hosted on Zoom platform. It has got some limitation of 100 participants in this live room. Anyway, this program can be accessed on YouTube. I hope there are people who are joining this program. And coming to this program, this webinar, I would like to congratulate Head of the Department of Chemistry, Dr. A.V. Ramesh Garu, and also Dr. Mamidi Gopi, who is the convener of this program, and every other member of this Department of Chemistry who are instrumental in organizing this program and also inviting experts from Apex educational institutions. I hope this program, Recent Trends in Chemical Sciences, definitely takes us along with the latest trends in the field of chemical sciences and will enlighten us with knowledge and also research developments in this region. This webinar reflects basically on the global research and also recent developments as far as this chemical research is concerned. And we have got wonderful speakers from India and also from abroad. I'm very thankful to the speakers for sparing their time and being in this webinar to enlighten us with their own expertise and exposure to the developments in their field. And I advise the research scholars and also students, it really gives us a wonderful experience to come together and also learn from international experts while listening to them. And you will come across many news and recent trends and also recent developments in the field of chemistry or chemicals. I hope, dear young students and also research scholars, you take some hints from the lectures and you will form the future, what we call aspirations and also goals to set your career in a right way. And I hope this webinar will also lead all of us together into the new vistas of knowledge and also research so that we can collaborate together in days to come. Above all, I would like to wish you all the best in conducting these deliberations through this webinar on recent trends in chemical sciences. Visakhapatnam is one of the fast changing and fast developing cities with many investments and also a lot of research in pharmacy and also chemical industry. There are many companies in and around Visakhapatnam. Above all, Dr. V.S. Krishna Government Degree College is one of the prestigious educational institutions in northern Andhra Pradesh, providing not only undergraduate courses, but also postgraduate courses as well as research. And we have got a good number of research guides in the college. Even Dr. Gopi and other members of the Department of Chemistry, they're also guiding research scholars. And likewise, the college is catering to the educational needs of the students. And programs like this are conducted day in and day out by the expert faculty members of the college, only to cater to the needs of the younger students and also scholars. Together, I think we can achieve some contentment and also what we call intellectual, what we call contentment through these programs. I wish this program a grand success, and these deliberations definitely would help each one of the participants to pursue their career. Thank you so much. I also would like to thank the resource persons once again for sparing their time and being part of this wonderful program. Thank you, and thank you so much. All the best.
ఒకసారి సార్తో మాట్లాడు.
Gopi, I hope you can go ahead with the program.
Okay, okay. Thank you.
Okay, I leave the meeting.
Principal sir, and now the session will start with the professor from IIT Bhilai, Dr. Raghavendra Garu. He is a good researcher, and he completed his master's from. He completed his master's from Banaras Hindu University. It is a central university, and PhD from National University of Singapore, and he was the All India Gate first ranker in 2009. Also, he has a good number of publications, and he was awarded a Humboldt Fellowship also, and he has good number of publication. One publication with highest impact factor, that is 45 chemical reviews. Now he is working in Indian Institute of Technology, located at Bhilai. Now he will share his research ideas, and will encourage the students in especially the chemistry research field, and he will interact with all the students, faculty members, and scholars. And Dr. Raghavendra Garu, and please join the session, and please motivate our students as well as our staff members and scholars. Give your wonderful lecture.
Yeah, I think you need to unmute his mic.
Yes.
పట్టే జూన్ ఉందట అకౌంట్ నాకు ముందే చెప్పాల్సింది కదా.
I can do that. Don't worry. I can do that.
Okay, sir.
Yeah. Sir, your mic is unmuted. Welcome to this webinar, sir.
Thank you. Thank you, Vijay Babu Garu. This is Dr. Raghavendra from IIT Bhilai.
Very good to see you, sir.
Same here, sir. Thank you for invitation and hosting me here.
Yes, sir.
So, sir, could you allow me to share my slides?
Yes,
So,
I hope you can.
it is saying that the host is disabled participant screen sharing.
Okay. Just a minute.
Sure, not a problem.
Sir, now please try to share.
Yes, now I could say that. Yeah, thank you.
Yeah, okay.
So, is it my screen is visible to you?
Yes. I think you can go to presentation mode.
So, which screen are you seeing? It is like one with a two screen, two.
Yes, both the screens are seen.
Both the two
And the
screens are
next
showing
slide
to
is
you.
also
Okay.
seen. Yeah.
Then I should just give me a minute. I just change something. Sorry. Yeah. So, may I know which one you are saying still see two screens or
Yeah,
one
still
screen?
both the screens are seen, sir.
Okay. Yes. Excuse me then.
Yeah, now it's into single
Okay,
screen
just give me a
again.
minute. I will unshare and share it again. Yes, I think now I think you would be able to see my screen properly.
Yeah, yeah. Yes, it's right.
Yeah. Okay. First of all, thank you a lot for inviting me, and thank Dr. Gopi and the principal, sir, which is like a Dr. Vijaya Garu and the head, Dr. A.V. Ramesh Garu. Thank you a lot for inviting me to this conference. So, yeah, this is Dr. Raghavendra. Today I will be talking about chemical materials for photoactuators through two-pressure cyclotron reactions. Okay, and currently I'm working in IIT Bhilai as the Gopi introduced, and I am working in two disciplines further now. One is like a department of chemistry, and I am also working on battery materials, which is like a department of discipline of electric vehicle technology. So these are the two departments I work. And yeah, when I was talking to the Gopi, he was mentioning like what kind of audience we are getting. So he has mentioned that like, we are getting mostly the undergrads and master students will be getting. So I have made my slides accordingly so that you could understand what I'm speaking a bit. In fact, like I will end with like some of the opportunities where you could get it in IIT. IIT or not only here in our IIT, any IIT. I just want to briefly introduce you like how our research works, as well as like what are the available facilities, and all these details will be given in the end. And if you have any comments or queries, please feel free to contact me in the email which you could see from my slide. Okay then. So I know most of you are not familiar with the Bhilai, but like actually this is one of the closest cities to the Vizag, which is like almost like 8 to 10 hours 8 to 10 hours from the Vizag actually. It is near the capital city of Chhattisgarh. I am pretty confident most of you are aware of the Chhattisgarh state, and this we are very close to the capital city of Chhattisgarh, which is Raipur. And this is one of the latest institute in India, which is specifically in IITs. So we are the youngest IIT in India, where we are established in 2016. And currently our transit campus is in Raipur, but soon by March, we are expecting to move to our permanent campus, which is like 30 kilometers from the current campus actually, which is not so far actually. And currently although we are a youngest IIT, we have already 6 departments and 9 disciplines, and we are already more than 1,000 students around. So which includes like various research scholars and master students actually. So with this, let me go into my presentation. So the motivation of most of our research comes from the nature. So I want to give you a few brief introductions to the how this nature is how inspired various researchers. Then I will go into my work, where you can see here there are 3 examples I have shown to you. One is ATP synthesis and kinase walking, and another is a flagellar motor. Okay, so in ATP synthesis, I believe some of you might have familiar with this, where is like this is the motor which generates the energy, which is like energy resources, which is like ATP from the ADP and proton concentration. So from there, like you produces ATP, which is a energy source of all the living beings, especially human beings as well. Okay, so this is a very interesting inspiration for us. Not only this, like again, like we go to the kinase walking, you can see here how kinase is walking from within the biological systems and moving very, very bulk systems from one part of the body to the other part of the body. And flagellar motor, again, it's the same thing. As you can see, there is a motor rotating, and accordingly there is a movement is coming up. So you see here, this is completely molecular level motions. And when we, these are the 3 gentlemen who have received the Nobel Prize in 2016, just by trying to got the inspiration, and then they try to mimic the same thing, or try to use the materials or chemical molecules to mimic the systems, and they have received the Nobel Prize. I will give you one of the example from the Bernard Feringa. So he has synthesized, he has prepared a molecular motor, which is like a molecular car. And how he synthesizes and designed the car, you see here, you can see a car, a body, which has been linked by the 4 functional groups. Okay. And when he shined the light, and all these functional groups can be activated, and they can move here from one place to the other, as you can see in the GIF file or that cartoon over here. And we can continuously control these motions by using the different excitations and continuous excitations, as well as the different functional groups. And I think you can also see a video here. Okay, there is some issue. Yeah, so I believe you can see a video here which shows that a molecular motor is moving from one place of the copper surface, which is like copper 1,1 surface, and it is moving from one part of the surface to the other part. It's like a moving your car from one place to the other place in the road, and we can do it. And we do have the steering based on like how we excite it, what are the functional groups we are what is the functional groups we are using, and how we design the system based on that the molecular car gonna be moving from one place to the other. So you can see here, it's like you can control the molecules into the molecular level and design the systems. But it is not a macro phenomenon. It's a completely molecular phenomenon. So application is going to be very limited actually. Okay. Then, so to, when any system, if you want to see the application, it has to be in bulk level. Then only it is easy to observe. Then what he did is like he has taken the similar molecule, but this time not many functional groups, but only one functional group, where you can see here there is a double bond, and upon excitation, what happens actually? So this single double bond, the double bond converted into the single bond in the excitation, and then it get relaxed and then get rotated. So you see here, this is a stationary part, and the top one, it will be keep on rotating, and that's how the rotor is working. And because of this rotation, molecule rotates. But later, what he did, he combined this one with the liquid crystal systems or liquid crystal film here, and then he could get the film. And in this film, upon excitation, we could see like the molecules are rotating, and because of this, the objects on this the liquid crystal film can be rotated. So as you can see, there is a glass bead which can be rotated, and now you can see this glass bead is in the molecular levels. In fact, like several thousands of big orders of bigger than its own size. So it is showing a very good mechanical motions. Okay, so this is completely motions in the molecular level. Now I want to take it to another example, which is like a spider or any insect. You can take it up. So here I'm showing a spider which is moving upon shining, moving from one place to the other, as well as jumping from one stem to the other stem. And what is the driving force for the movement of this? It's completely stimulated by the muscle strain. What do I mean by muscle strain? So you see here, the spider is moving just because it creates a strain in its legs and releases this stress in a specific manner, so that the spider is moving from one place to the other. This goes to the same to the human being as well. We do generate a strain in our muscles, and when during the process of controlling release, and we could walk from one place to the other, and we can stand, everything we can do it. Now, this is again a very interesting biological phenomenon. Can we design the systems or chemical material which can behave the same? So yes, we can do it. And recently there is a huge amount of research is going on. But instead of like a muscle strain, where we have a biological system, we have the muscles, but in case of the materials, you don't have this. So you have to be stimulated by various motions, such as like various means. One is like light, heat, mechanical, and force, and so on and so on. And today I will be mostly focusing on the light. Of course, I will also briefly introduce you over the heat and mechanical force, so that you understand what we are talking about. But to look at this, do we need to have very complicated chemistry? Actually, not really. So whatever the chemistry you are studying in textbooks can be used, such as like pericyclic reactions. So I'm pretty sure most of you are whether you are undergrad or postgraduate or any other like professors, and everyone knows the pericyclic chemistry, and you are very familiar with electrocyclic reactions as well as the cyclohexane reactions. So let me briefly give you electrocyclic reactions, where you see here there are 3 olefin groups and which are conjugated and next to each other, right? When you're shining the light, and these 3 olefin groups can get undergone the photoreaction and get cyclized and forms a cyclohexadiene, right? And upon heating it, it comes back to the cyclotriene. So this is one of the systems where you can easily understand how, which I will demonstrate you how it can be used for the preparation of a photoactuators. And the next one, of course, is one more important thing before I go into cyclohexane. You can see here this is a planar molecule. After this, this is converted into non-planar because these 2 new protons which are coming up, they're coming into the sp2 to the sp3 hybridized orbitals. Then the shape of the orbital going to be changed, so from planar to the non-planar system, which I will explain later. Then again, we come to the next system, which is the cyclohexane reactions. I'm pretty confident most of you are very familiar with the 2-plex cyclohexane reactions. So you see here, there are 2 olefin rings, olefin bonds, and shining with the light, they undergo the cyclobutane, and then can form different isomers. That's we will be briefly, significant part of the talk, I will be covering this because this is where I'm really working on. And in addition, I will also briefly introduce you for a cyclohexane reaction, where you see here butadienes is undergoing the photoreaction and forms a cyclooctadiene actually. It's not only in these systems, we can also do the similar 4+4 cyclohexane reactions in the anthracene as well. You see here, your butadiene can be absorbed here. If you ignore the rest of the part, you see here one olein, another olein, and you have one butadiene, other butadiene here. Upon shining with the light, then you get the product such as this. So it's again a cyclooctadiene based systems. So of course, this is not a diene based system, but it's a cyclooctadiene is present there. Okay, so you see here, these are very simple reactions, right? And we do study a lot in the textbooks. Okay, so let's discuss how these reactions are used. However, I would like to emphasize before I go into next slides that almost all these reactions, what you study in your textbooks, are completely performed in the solution state. Okay, but once you bring them in the solution state to solid state, which is like mostly I will be describing in the crystals, such as like gemstones, might be you are familiar with these, such kind of crystals I will be showing you. The complexity goes involved. However, you don't need to worry for now. But you see here, there is a lot of rules are coming up, but you don't need to worry. Again, these are very simplistic reactions, very quantitative in nature, means like the reactions are very 100% undergoes and so on. Yeah. So let me take you one of the example of the electrocyclic reactions. So this is a molecule you see here. This is a thiophene ring and thiophene ring, which are bridged by the olefin cyclopentene base systems. So if you look into the olefin bonds, so olefin, there are like olefins are conjugately arranged, and they are again in the more or less in the planar mode. Okay, when we shine the light, these olefin, three olefins, conjugated olefins, undergoes the electrocyclic reactions and forms cyclohexadiene base systems. Okay, so previously it was since all the carbons are in hybridized in sp2, it's a planar. But after the photoreaction, sp3 carbons are generated, so it's not planar. So the strain is created. Again, coming back to the original, so you have to create a strain, and that strain, when they are released, so this is the asynthesized crystals, and upon shining with the light, so it's a planar molecule. Here the molecules are planar. Upon shining the light, there is a strain created here. So you see here, this is square, very nice square. Now it is converted into the rhombus structures. Okay, same goes on to the other structures, where you see here we had it was done a slight modification over here, where you see here previously it's just thiophene, but we are increasing the azure group inside the systems. So same thing is observing. Of course, meanwhile there is a change in the electronic structure. That's the reason color of the crystals change. That's a different story. So the same examples it has been published, and then we see there is a change in the shape, which we have discussed. Then how else this has been used? So this has been used as a instead of taking growing as a block shaped crystals, if we take a needle shaped crystals, okay, then shine with the light, instead of converting this perfect square to the rhombus, now the crystal started showing the bending behavior. See, previously straight, upon shining the light bend, and you irradiate it with a higher wavelength, you release it you don't irradiate it any further, it will come back to the virgin shape. And again shine the light, it gets bent and come back. So it continuously happens. It happens almost tens of times. Then what's application of it? You can take an object such as the black particle here, and if I put the particle here and shine the light, it kicks away. So the object moves and comes back, and you can keep moving the objects. And I will show you several videos which I hope you will excite you guys to understand what's application of this. So is it only like a bending behavior can be seen, or can we do anything more? Yes, we can do and many things more. So instead of just bending, you can also get the spiral. How do we do it? Instead of we have to exit in a specific angle. So if you exit at 0 angle, it will be spiraling. But if I'm increasing the angle, the spiraling behavior is getting changed. So your spiraling will be how the spiral will be controlled based on the angle of irradiation and the photoreactions. Okay. Then I have told you the crystals are bending and so right. Now let me show you a video about it. So there is a crystal here, and upon shining the light from this direction, you see the crystal is completely bent. It's like a like plastic rubber, and by force you are bending in such a way that it looks. Okay, and again you release it, it will come back, and you shine from the other side of the crystal. Again, it shows like bending in the other side, and release it, exit with the 500 nanometers or visible light, or release with the time, and you can come back to the virgin shape. So you see here, it's a bending is a max, very much significant. Okay, so this is a very interesting phenomenon. Okay, then next you see here, we are currently using one molecule, and we have it was not our work, but it was from the Iris and Japanese work, where you see here there is there are different substituents they have been using it. Now they have changed the substituent from the phenyl ring to the anthracene ring. You can see here anthracene ring. Not only with this, previously you are using one pure molecular system. Now I am including another molecule with the perfluoronaphthalene systems. So in this case, you get a perfluoronaphthalene systems, and you got the crystals. And again, even with this perfluoro system, it undergoes the electrocyclic reactions, as you can see here. Then when we shine when they shine the crystals with the light, you can see here the crystals are going to start bending. Then it's just bending. So what's the application of it? Okay, so the application comes again here. You can lift heavy metals. What I mean by that, you see here you have a crystal, and you stick with a very heavy metal ball and shine the light from the bottom. So let me show you a video. So you have a crystal, and you keep a metal ball and shine the crystal, and you can lift heavy weights. So now now you could see crystals which can move weights, and which could be used as a weightlifter sometime. Is it okay? Now we have another question. Like, is it only one-dimensional motion? As you can see, like I'm motion from one to the other, I'm coming back. Is it only one-dimensional motion? Actually not. So if you look into the system, it's not only rotates, bends in one direction. You see here, you have a crystal. Previously, what happened? If I'm looking at the top, okay, from the top, I'm looking at it. So if I look at the top, you see only this part, such as this. So if you shine a light, it can move from one direction to this direction, or it can back to this direction. Not only this, it can also move in the perpendicular direction this way, or otherwise I can rotate in the triangular shape. Okay. Then what is the importance of it? Why is like you need to rotate in 3 dimensions sometimes? You can use it for moving various objects such as like gears. So I believe most of you have seen like gears in your cycles or motor vehicles. So so we press it and it rotates, right? Now we could move the gear by using the crystals. So you can see here, we are with alternate shining of the light. So the crystal is moving and it is rotating the gear. So this is a way we can easily convert the light energy into the mechanical force by using the chemistry. So far, most of the applications are done by the the mechanical engineering people or electrical engineering people, but it's when you come to the chemistry side, it's very limited. So now we are in the forefront of the whole research world, which is again, which matches with your title of the today's conference, which is like a research trends and chemical engineering, chemical sciences. You see here, previously chemistry is more like a supporting science, but now no longer we are a support science. We are the we generate the technology which can be directly applied in the real life, such as like you can see here, where we can convert the light energy into the mechanical force and convert the light energy, like you can, maybe it can be sometimes used as a renewable light resource, where you can convert the sunlight also converting into the mechanical force. So this is regarding some of the examples I would like to present to the pericyclic reactions, such as like electrocyclic reactions. So let me go into the next example, which is like for 4+4 cyclation reactions. Again, I have mentioned like a 4+4 cyclation reactions in anthracene. You see here, there's a diene systems in both the anthracenes. Upon shining the light, they undergo the dienes undergo the cyclization and produce a another system with something look like this. Then, so if you look into the crystals, you have a crystal of this, where you have anthracene crystals are aligned, anthracene molecules are aligned very nicely. So in the single crystals, and upon shining the light, these anthracene planar molecules convert into the non-planar system. So this is a single crystal structures. So if you are not familiar with the single crystal in your view, this gives you the really atomic positions and what happens in the crystal completely, it generates it. And how whatever you see the molecules is a planar or non-planar system, it can be easily seen from the single crystal structures. So this is a single crystal structure you see here previously, completely planar molecules. All right. After the photo reaction, what happened? This this 9 and 10 position is converted into the sp3 hybridized, which is a non-planar, and the phenyl rings which are attached to these systems are moving away from the plane and generates a strain. Again, remember, whenever there is a strain, generation of a strain, and the objects are meant to show the mechanical motions. So you see here previously it's a plain crystals, plain needle-like crystals. Now it gets paralleled. And if you leave it for time, so the reversible reaction take place, or like you irradiate the 254 nanometers, or you irradiate the room temperature for some time, reversible reaction will take place, and then you get the crystal into the normal shape. So you see here, you can convert the light energy into mechanical force and come back to the original shapes. Okay, so this is completely of the pericyclic reaction, specifically electrocyclic, as well as the 4+4. There are a lot of examples in the 4+4, but with a limited time, I would like to go into the other cyclation reactions, which is going to be the crystal. Okay, so this reaction is completely actually when I was doing the research in Singapore, and it was a very serendipitous, means which is very accidental actually. So it's a kind of a eureka situation where we have tried to produce a metal complex, which is a very simple metal complex, where you see here zinc is reacting with the benzoic acid as well as a pyridine-based linker, which is like we call it as a 4s3 linker. Then when you crystallize this, we get a metal complex such as this, where you see here zinc is present in a square pyramidal geometry. I'm pretty sure most of you have studied like zinc can adopt various geometries. Here in case of this, it's a square pyramidal geometry, and there are two zincs which are present in the square pyramidal geometries, which is we always call it as a pedal wheel structures. And where you look into the zinc is bonded by the carboxylic acid or oxygens of the benzoic acids from here, and from the square pyramidal, and apical sites, which is axial site of the zinc, is bonded by the pyridine of 4s3 linker, which is the nitrogen is the donor, lone pair donor. Then you get a pedal wheel structure like this. This is a one molecular system, one single molecule. But if you look into the solid state, again, everything is we are creating into single crystals or solid state. So you see here, this molecule is aligned with the next, always need to be packed with the next molecule. So when it is getting packed, so one of the system, one of the 4sp is interacting with the next 4sp in head-to-tail manner, and the distance between the olefins is almost like 4 angstroms. Again, single crystal structures gives you a lot of details, including the shapes and atomic position. Not only that, you can also calculate the distances, how far and everything. Okay, I'm explaining this because like I know like some of you undergrads as well as masters may not know the advantages of the single crystal XRD. So this is a huge advantage. You know all the structures, how far the distance, everything can be detailedly. We can obtain all the information can be obtained very detailed manner in the single crystal structure or single crystal X-ray diffractions. Okay, so now you see here there was like a olefin rings are arranged, and these are planar molecules. As you can see, all whole molecule is a sp2 hybridized. Now when we shine the light, these olefin groups are double bond C undergone the photo reactions and forms a cyclobutane. Okay, again two pleasure cyclation reactions, so which leads to cyclobutane. Again now upon cyclobutane reaction ring formation, you see here sp2 carbon converted into the sp3, and it got the molecules started bending, and then since because of the bending there is a movement of the rings, like previously it was plain, now it is moved away, there is a strain created, and this strain has been used for the mechanical motion. So again, as I say, like these are mechanical motions, which was a it was a serendipity. When we are doing these reactions, we see here the crystals are starting showing the motions. We see here the crystals are getting rotated and break into the two pieces, as well as the explosion of the crystals into pieces. And this is the bulk of the crystal. If I put a crystals and if I shine with the light, and you see the crystals are showing this kind of thing. Now, I would like to mention to you one thing. I'm pretty confident some of you might have seen similar phenomena in your real life. However, you are not exiting with the light, but what are you doing in our life? You heat it. Where do you observe it? It looks like a popcorn. I'm pretty confident most of you are familiar with this. So you see here, you take a corn and put it in a hot place and you heat it up. What happens? The corn will be breaking and jumping and moving away. Okay, you see here, this is the same phenomena we are observing in this mechanical motion of the crystals under UV light. So only thing is, instead of like heat, we are using the light. Again, you see here, it's completely laboratory based. It's not natural phenomena. So we can do a lot of fine tuning, which will coming in the following slides. So anyways, we want to see what kind of motions are observed and things. So we have taken the crystals and one after other with the high-speed cameras, which is like 5,000 frames per second. Our normal cameras have a rate of like 30 frames per second, but we have to observe every phenomena which is very fast. So we have taken a high-speed camera, which is like which can capture up to 5,000 frames per second. And when you take the crystals, and they are started showing rotation motions. So it's called as rolling and moving. I believe you have seen road rollers where you can see the such kind of rolling, right? Same thing phenomena we can observe in the molecule, in the crystals. And breaking into two pieces and explosions. So all these are the typically three motions we have started observing. Okay, now this is interesting. Now we could see the crystals and we should see like we have been seeing the motions are observed. Now we need to establish why is the motion is observed. Although we have empirically says like, yes, the photoreaction is taking place and that's really happening. But now we really need to quantitatively and very rigorously need to establish that. So for that purpose, we have taken the crystals. Again, as I said, single crystal XRD is one of the very powerful tool to find out what is happening, how much is the photoreaction is taking place, what is happening in the molecular level, it can be easily found. So these are molecule before the photoreaction. You see here, these are the olefin bonds. And upon UV light, so slowly almost 21% of the cyclobutane formed along with your olefin groups are still present. And further UV radiation, it forms a polymer, 1D polymer. You see here, previously there is no cyclobutane at all here. It's completely cyclobutane. Now there is no olefin at all here now. Right? So you see here, metal complex to the one-dimensional covalent polymer has been established. Now, meanwhile, you see here the density of the compound, which is like 1.52 angstrom per cc, shifted into the, reduced into the 1.37 gram per cc. You see here, so the density of the crystals previously very high, converted into the very low density. Again, let me correlate again with the popcorn. If you remember, popcorn, before it converted into the popcorn, the corn kernels, I mean like the corn kernels are very tightly packed. But once it got popped, you see here, it get opened up, the density got reduced significantly. Again, same thing is happening from high density system to the low density systems. And this is the same thing is happening. And this again, I'm showing you like what was happening here, the circulation reaction I want to project it to you guys. And again, I need to establish the phenomena well. I don't want to go into the more details because I'm confident like some of you are very undergraduate level, so I don't want to go into more details, but like let me show you. When I take a crystals and put it in the oil, because I had to put it in the oil, otherwise what happens, the crystals will jump away, right? I put it in the oil and shine the light. So you see here the cracks are very specific in specific axis. And I'm pretty confident most of you are very familiar with the HKL values or Miller indices in your school. So if I correlate these axes cracks into the Miller indices, which is going to be in the direction of 110 or -110. So when I look into this and correlate with the molecular structures, you can see here that they're along the molecular arrangements, such as like olefin volumes. So whenever they are aligned, that place they are showing that direction. They're showing the mechanical reactions are taking place, and the cracks are coming along the direction. So confirmed now, it's almost 100% confirmed that. So wherever there is a double bond in the arranged manner, that's the place the crack is coming, and because of that crack, the crystal showing the mechanical motion. So now we have successfully established and explained the photosalience. I mean, like establish how the crystals are showing the mechanical motion. We have successfully established. Now, so this is again accidental phenomena or a serendipitous, or is it like a eureka situation? Now we want to establish, we want to go ahead with establishing new materials with these principles. And other way, we are chemists, right? How do we design the systems? So as I mentioned, there are basic principles for a photoreaction to take place. Usually in case of solution state, where we study in textbooks, we don't discuss this. But if you look into the solid state, there are some rules. So whenever why these rules are there, but in case of solutions, the olefins move, or like molecules move randomly. Whenever they come closer, they undergo the photoreactions, and after that, like they go away. After the photoreaction, the molecules whichever come closer, they can move together, or whichever not reacted, they go move away. But in case of solid state, the molecule doesn't have that freedom. They are restricted. So they cannot move from one place to the other. They have to be strict to the place where they are there, right? So in such cases, the photoreaction need to take place, and they have to have some specific rules. The first rule is the separation between the olefins should be less than 4.2 angstroms, 3.2 to 3.5 to the 4.2 angstroms. And secondly, the crystal should allow slight movement of the molecules or atoms should be taken place. So the crystal should allow it. So this was established in 1970s by the Schmidt, German scientist, and that's where we call it as a Schmidt's rule. Now we know the rules, how to a compound to show the photoreactions, and how to design the system. We have the basic fundamental ideas. Now we went back to our accidental or our serendipitous observation or finding. Then we see here this is a compound zinc, which is a metal, and photoreactive linker and supporting linker. So after this, we got a metal complex coordination polymer, and we show the mechanical motion. Now we have taken the same thing. We taken the metal as a silver now, changed from the zinc to the silver, and we have taken the same photoreactive linkers. We don't want to change it. We have totally 3 linkers, as you can see here. I'm drawing them figures here. And instead of supporting linker, which is organic, we have changed it to the inorganic because of we want to get into the less complex situation. Because usually aromatic system will give you a decently complex. We have the different substituents, their rotation and the packing is a little complex. So we want to come to the very simplistic manner. So we have taken this. We have it silver as a metal, 3 counter anions, which is like BF4 minus or chlorate and nitrate. And we have 3 linkers. So we have 3 supporting link counter anions and 3 linkers. So we have 3 versus 3. So 3 by 3 is going to be 9. 3 into 3, 9, right? 9 permutations and combinations. And with this situation, so we have produced all the 9 compounds. very successfully. And I have shown the one of the crystal here with the PF4 with the 3F. Okay, this is a compound I have shown you. And when we have taken the crystals and shined with the light, these crystals also showing mechanical motion. Here they are jumping and they're breaking into pieces and they are jumping further. And we have taken the crystals again and under microscope, again high-speed microscope, and they're showing like jumping into the, moving away from the focal and coming back, or moving from the outside the plane, outside the focus. So now we have taken the systems, we have designed it, and we could see the similar motions. Again, we need to establish whether the density phenomena or strain in the crystals is same with the other systems. Yes. And for that purpose, what did we do? We have taken all the listed all the compounds, and we have taken the all, when we look at it, all are undergoing the photo reactions. And is it all showing the photosalience or photomechanical motions? Actually not. Out of 9 compounds, only 6 compounds show the mechanical motions. The rest did not show it. And again, we try to look into the like density calculations, density change, or percentage volume change. In that cases, where we see here, whenever there is a significant density change, whenever so significant changes happening, density changes happening, then they show the mechanical motions. Otherwise, they don't show any mechanical motions. Yeah. So that's a basic thing. So now we have established like we can design it. Again, this is completely of metal complexes. Now we want to go into the one-dimensional polymer. I believe most of you are familiar with what is a polymer. In case of this, what do we do? We have taken lead as a metal, again metallic, and your photoreactive linker, 3F4SPY, and your supporting linker, which is a bromide. Okay. Then when you crystallize it, you see here lead, which is bonded by the 4SPY linkers and bridged by the bromide linkers. I'm pretty confident you have studied in your textbooks like bromide can act as a monodentate linker as well as a bridging linker. So it can bridge the metals. Okay, so here the lead is bridging the metals. There are 2 bromides which are bridging it, and this bridging is continuously happening in one-dimensional. That's why we call it a polymer, one-dimensional polymer. But it's everything is a coordination bond, so we call it as a one-dimensional coordination polymer. Okay, so now these 4SPY linkers are which are bridged with the coordinate with the lead. Again, these are bridged by the and one lead is bridged by the bromide. Then the distance between them is again less than 4.2 angstroms. And because of the coordination and within bonded to the one-dimensional polymer, and they're along with the same directions, the olefins are very well aligned. When we shine the light, they undergo the photoreactions. How do we prove it? Again, we can take it to the single crystal study or the NMR studies. NMR, I'm pretty confident most of you have studied in your textbooks. Whenever there is a cyclobutane formation take place, almost you get around new proton around 4, which was not present before. Previously, there was no cyclobutane. It's completely aromatic. Since it was completely aromatic and delocalized, you get protons only in the aromatic region 6 to 8. You can see 6 to 9, all you can see here. But after the photoreaction is taking place, cyclobutane is forming. Once the cyclobutane is forming here, so you get a saturated carbon with the proton. So whenever you get a saturated carbon which is attached to the proton, you see here you get it in around 4 angstroms, 4 ppm. So as the photoreaction takes place, you get a new peak, and this is present absorbed into the 4. And you see here wherever the other protons, which is like A1, which is like unreacted system, completely gone away. So you see here and it undergone the 100% photoreaction. Okay. Now now we have seen it. It's showing the 100% photoreaction and everything. What kind of mechanical motion we can show it, right? So the question now here we can see it. It can show very interesting mechanical motions such as the photosalient behavior in 4 different modes. One is a photosalient effect, bending, splitting, and twisting, and curling. I will take it one after another. Before I go into it, these are the 4 different motions. How do I know that I can control it, right? So I need to know like how to control it, right? So how do I control it? By controlling the size of the crystals. So if I grow a big crystals, they show you a cracking and explosion, which you have seen previously. You see how there was cracking and breaking into pieces and so on. This is usually whenever you have big crystals, it shows this phenomenon. But when I have the smaller crystals, they show you a bending and twisting and curling. I will show you again what I mean to show you. what I'm speaking it. So when I have thicker crystals or bigger crystals, these are the photos where you see here the crystals are breaking into those big crystals are breaking into small crystals and borders. Okay, so these are videos where you can see here you have crystals, and when you shine the crystals are bending, and at a certain time the strain is so much high, so they start breaking and into small pieces. So you see here how the crystals are jumping away from the focus of a microscope as well as they are moving away. Okay. Okay, and I have one more thing I would like to highlight here. Since these crystals are breaking into small pieces, in fact, sometimes into the powder, you cannot use them for the single crystal analysis. So final structures evaluation is very difficult. We only do the indirect method such as like NMR to confirm the structure is what kind of structure we are getting. However, we could still establish it. And yeah, that was the photocell behavior of breaking of the crystals into the small pieces when you have the bigger crystals or thicker crystals. But when I take it to thinner crystal, what happens? Now you see here there is a crystal here, and shine the crystal along only this direction. You see here the arrow side, and they show the bending into the very curly nature. It bends and come back. Again, I'm showing the axis, so shining the one direction. You see the crystals are showing like motions, and after some time, it get like maximum strain is generated. And after that, it start to relax. So once you start relaxing, it comes back to the curvic shape like this, as you can see in the video photo here, and which you can observe also in the video. And this is completely happening because of the photocycloadhesion reactions. Right, now it comes to like almost original shape of this like curly in nature. Next one. Now I am moving from shining the different sides, right? And one side and the top side. Now if I put it towards a point, if I shine it, what happens? So when I put the towards a point, you see here the crystal will crack into two pieces and they get curvy, or like they get into the twisting, actually splitting as well as the twisting. You see here that we are shining the crystal here, and they get split into two pieces and they get into the twisting. Again, it's completely because of the very simple two-crystal cycloadhesion reaction. Only thing is how the crystals are reacting. So what happens actually here? When I'm radiating from the top bottom, the whatever is molecules come closer to it, undergo the reaction first, then the reaction will go further in from the bottom to the top. And during this process, the strain is created, and because of the strain, the started showing bending, but during bending because of the strain, and the strain is literally leads to this process. And when you look into like bulk crystals and you look into the bulk crystals, it shows all the curling and such kind of this way. Okay, now we see a lot of motions. Now how I can move an object, right? So for that purpose, what did we do? We had taken one glass rod and put it in among the crystals and shine the light. So this during these motions, you see here within a few seconds, the glass rod which was present some time below, it moved to the upside. So you see here there is a movement in the crystal, movement in the glass rod because of the photoreactions. And so this is a basically thing. Now we have taken the crystals and we could show mechanical motions. Now it was completely driven by the photo reaction. Now I want to take it to the like again like can we do any mechanical force, because so far we had talked about like stimulated by the light. Now I want to take it to like stimulated by the mechanical force. So what I mean by mechanical force, I want to apply the force and see if there is a bending. So I have a crystal here, I stick to the one side of it and I want to move it from the other side. So you see here I'm moving it and they can bend. So these are forceps we are using and moving a crystal, and you can do a lot of mechanical motions. So it's all these motions again. I'm taking the crystal, I'm sticking here, and I'm moving one. Previously it was clock, anti-clockwise. Now I'm moving the clockwise, and you can easily bend without any problem. And once you release it, it comes back, and I can combine this and I can make a loop. Why I'm making one? I make a loop. I can write a normal names. You know, you can see here P, E, and several things can be, I can write a lot of names easily through this process. Okay, so this is a mechanical motion of it. Yeah, so far we have seen a lot of motions and we could generate this trend. And by the way, why am I really highlighting it here? Most of you are very familiar with the crystals are very brittle in nature. So it's like a glass rocks, you know, you might use in the laboratory or you see in our real life ways in the classes. When you try to bend it, they break. The crystals, single crystals usually behave the same, but these are very specific crystals, but very specific crystals, and they show the specific mechanical motions. And I have been keep on mentioning to you this, we always establish the structures by the single crystal sardine, right? So whenever we show the mechanical motions in the single mechanical motion, always we lose the crystals and we cannot establish the what is the reaction is happening. We use the indirect method such as NMR, and because from the NMRs we can establish that yes, this is happening and this is going to be the structure of the compound. That's why it shows the mechanical motion. But single crystals are one of the important and direct tool we can establish the similar phenomena. But most often what happens, our single crystal breaks and we don't able to see the final structure. But fortunately, we have observed crystals. We have designed, actually we have designed and obtained observed crystals where you can see here the crystals are present. And even after the photo reactions, you can see the cyclobutane formation is happening. And even after the mechanical motions, you can see the crystal is survived and show the mechanical motion. So these are the motions. So again, we have taken the videos as you see, like the bulk and big crystals and shining with the light. We are shining with the light, the crystals are breaking and into small pieces and jumping from one direction to the other. We see here the speed of the crystals, they are jumping very, very fast. But most of the times what happens, the crystal will break into small pieces or powdery. We cannot get the structures, but fortunately here, some of the crystals, even before completely become powdery, we could able to separate them and measure it, and we see the 100% photo reaction is taking place. Okay, now we want to see like what kind of motions are there. We could see like they are splitting and flying, as well as rolling and jumping. All these kind of motions are observed. So what was there happening? We had taken the bromide to the iodine. We see that. Now we want to take to the pseudo halides, and we still get able to see obtain the one-dimensional polymers, and then we can get the crystals. And when you get the crystals and shine with the light, they also show the mechanical motions, right? So these mechanical motions are well and good, and they are bending and things happening. Again, here is what's the stimulation? The stimulation is bending of the crystals for a reaction, right? Now I want to heat it. It's like a popcorn, right? Now I want to change the stimulation from the light to the heat. In the previous slide, what did we do? Light to the mechanical force. So you are applying the force, then they are bending it, right? Now I don't want to take the crystals into the just like bending. I want to take into the heat. It's like a popcorn. So I take the crystals and put it under the microscope and heat it, and you see the crystals are like bending. You see here the crystal is going to bend and come back after cooling. Bend when you heated it and cooling. So you see here there are a lot of bending and relaxing into the original shapes continuously happening. Again, what is the stimulation? It's thermosalins or like heating. So you see here, we can observe the mechanical motion not only by the light, we can also observe the mechanical motion by the heat as well as the mechanical force, which we have seen in previous slides. And currently we are working in the similar, I want to skip this slide for you. This is a very similar phenomenon. Now I want to come to our current work in our lab as well. So we had taken to the original system instead of halides, where we keep on using it. We want to use the benzoic acids again, but we want to use the fluorine. I believe most of you are very familiar with the halogen interactions, right? Halogen do interact. And in case of this fluorine do interact. So this fluorine interaction, we want to use it for observing some phenomena. And we have got the complexes such as this, where here in case of previously, zinc was in penta-coordinated, right? Now it is in the tetra-coordinated, and it's like tetrahedral geometry. So 2 oxygen of benzoates and 2 pyridine rings, and it causes the tetrahedral systems. And when we look into the structures, you see here the olefins are separated by around like 4 angstroms here, as well as 3.7 angstroms here. Okay. Now, so these are less than 4.2 angstroms, right? So when I'm shining the light, they should undergo the photoreactions. Yes, they do undergo the photoreactions. In addition to this, they do show mechanical motion. So far, you have seen like show the mechanical motions so in one directions. Now these crystals are different. They show two different mechanical motions. You see, first they bend one side and immediately come back, and they rotate. They bend in other directions. And at the end, one single linear shape crystal convert into very bendy, curvy structures. And the mechanism has been established here. So we have a crystal rod. When you shine it, you produce a dot kind of structures, and then after that, it will bend back again into this shape. Okay, so this is a structure mechanism we have established. And when we take a very thin crystals, okay, previously it was a decently thick, but when you take a very thin crystal, you see here, it behaves like a one kind of like some kind of like worms in water, you know. You see here, they worm like bent and coming back. So such kind of motions which we see in the phenotypasting flagella type motions, like you see here, they're moving, right? These are similar motions we have observed. Okay, so overall, let me summarize for today's lecture. We have prepared various systems, at least in our work, to crystallize. We have used various metal photoreactive linker and supporting linkers, and then we have established several complexes, which shows like a multi-responsive behavior, which is like a photosalient, mechano-responsive, thermosalient behavior. And we can use organic systems where we have more parameters, and we can get like one-dimensional condition parameters and so. So overall, I would like to summarize where we have successfully designed photoresponsive materials through pericyclic reactions, which is very technical chemistry, and use them into the applications here. And for this purpose, we have used electrocyclic reactions, as well as the cyclohexane reactions, such as like 2+2 reactions, as well as the 4+4 cyclohexane reactions, and which can use, which can replace the engineering devices, such as like actuators to the chemical devices, where you can move the objects and convert the light energy into the mechanical energy. So this is the summary of my work. So let me briefly introduce about our institute also. Actually, although we are one of the youngest institute, we have the best facilities in the world, and these are not necessarily in India, we have the best facilities in the world. Why I'm saying best facilities in the world? If you go to any established places, right, you get one of the old machines with like hundreds of students are with you interacting with the system. So if you want to access the system, you cannot access it, and you always use the one of the old system to establish your chemistry. But now, since we are being a honor in the youngest institute, we are establishing the latest technologies. So previously, if you want to do the single crystal excited, which I have been showing you, previously we need to take up like half a day or 1 day to measure the single crystal. Now I can get the best system, which is like within 15 minutes to half an hour, I can get the crystal out of crystal structures. Like this, we have best facilities in our institute, being the youngest institute in India, and we have various facilities which are like the cost of these systems are very crores of money. And since we are youngest, we have very less number of students. So you, since you are gonna, if you are get the opportunity to join in our institute, you can easily access our institute yourself. Because previously, if you look at established places, you are not given access to the machines. But here we will be training you, because you are the one of the youngest, and we want to train you well here, and you can directly get hands-on. And once you get the hands-on, you can easily explore your knowledge on the field, and you don't need to be stay in the queues also, because like if you have hundreds of PhD students around there, you have to wait in the queue, sometimes even months. We do, fortunately, we get the samples from the various old generations, you know, IIT Hyderabad, IIT Kanpur, IIT Bombay. We get the samples from them. We do, because we have the people over there has to wait for like months sometimes for measurement. But here you give the sample within a day, we will measure for you and send it, because we don't have such a mental load. So overall, you can see here we have a lot of facilities, and we have various opportunities, and we can directly train you on the machines. So for this purpose, if you want to join us, or especially the who are who are studying in undergrads as well as masters. We have various opportunities specifically for higher education opportunities. If you're an undergrad student, you can join us into through the masters to the JAM. So in this case, you can join not only chemistry. Remember that you are not limited to the chemistry. You can also join us through the electric vehicle technology, where we do a lot of battery fabrications, and where like electric vehicles, right? You have been seeing everywhere. So you have to use the battery. Battery again, we have to design by a chemist, and I am one of the person who designed the batteries and who study and work on it. And we also work on material sciences, and you can join all these departments through the masters. And you can also join as a PhD fellow here again in the same departments like chemistry, electric vehicle technology, and material science. So what are the qualifications you need to apply for the PhD here? You just need to qualify the GATE. You don't need, like, if you just qualify the GATE, you are eligible to apply for the attend the interviews and get the fellowship. Or again, you have to have at least net qualification, net JRF LS. LS is good enough to start with the application if you couldn't clear the CSI JRF. And if you can't qualify both, but if you are working in some institute or like some companies, I know like we do receive a lot of applications after, although they join in the institute, a lot of companies where they get like salaries of like 15,000 or 20,000. It's not very minimal, and you have to work a lot. And end of the day, you don't get any degree out of it, right? So in case of this, we give the fellowship almost like 30 to 35,000. If you have like 2 years of experience, you can 35,000 as a fellowship, and along with it, you will get a degree after your education or your working. So this is where you can support your family if you want. Of course, I myself coming from one of the lower. I'm from I have studied in government college, schools, and I have studied in one of the very small colleges, and finally I could able to study well and get the GATE ranks and move to the higher education for various institutes. And of course, the main motto was that time is most likely study the higher education, not only get the degrees, I want to get the fellowship to support my family. So that way, we used to get the fellowship for the PhDs and get the supporting the family. And yes, I have studied in Singapore because those days they used to give me the fellowship of like 8,000 or 12,000 rupees. Fortunately, of course, when I joined, it was like 12,000 actually, 12 to 16,000. I don't exactly remember, but it was so less to support the family. So for those candidates, so low, so I had to move to the Singapore where I get a decent amount of fellowship so that I can support family. But nowadays, Prime Minister has established one facility, it's called a PMRF. Okay, so in case of if you are one of the top and if you are eligible for this, you can claim fellowship of up to like 80,000, which is like equal to the software techie guys, In case of chemical industry, no, chemical industry will give you 70, 80,000 with a master's degree or undergrad degree. But you get here, you can be a PMRF fellow and you can get the 80,000 fellowship, which is like equal to a techie guy, one of your software colleagues, if you have software senior, brothers and sisters, if you have. So you are getting much more than them actually. And along with that, you are getting a degree, doctorate degree, which is a very, very prestigious. So these are the various opportunities in our institute. If you are interested, you can join us, and I will give you my email address. If you have any queries, you can contact us. And with this, I would like to also acknowledge my students who are who are executing these projects, like Akansha, Aditya, and Uma, as well as we have collaborators and my funding agencies like DSTCRB as well as IIT-VIJAYA. And soon we are going to visit, moving to our main campus, which looks like this. So if you would like to join us, it would be one of the honor to have one of the youngest IITs as well as one of the newest buildings and newest facilities to be explored by yourself. And with this, I would like to thank you all for your kind attention. And this is, if you have any queries, you can contact us in this through email or any other places. And I also would like to again thank all the organizers for a wonderful organization of this online seminar, specifically Dr. Gopi, who is my close friend and my classmate. And if you have any queries, you can directly reach me, or if you can't reach me directly, you can also reach me through the Dr. Gopi always. And I also would like to thank principal sir, which is Vijay Babu Garu, as well as HOD A.V. Ramesh Garu. Yeah, with this I would like to end my lecture. Thank you. If you have any questions, I would be happy to answer them. Gopi?
Hey Raghav,
Hi.
how are you?
Any questions, students? If you have any questions, you can just comment or you can raise a question so I can address it. Yeah.
Raghav, one second. There is a issue. This is Apu. Yes, yeah.
Anyone have any doubts regarding career and research? You can interact with Professor their students, scholars, and faculty members. Any one of you have any, you want any idea regarding research? You can interact with Dr. Raghavendra. Hello, Raghavendra? Are you there? Hello.
Raghavendra, you're muted.
Hello.
Gopi, you can unmute him. You are the host. Gopi, you need to do it. Please unmute Raghav.
Yes.
Okay.
Yes. Yeah. Thank you. It was like I don't know what happened, but yes. It got muted myself.
Okay.
There is a restriction. Otherwise, everybody talks now.
Yeah, got that.
Okay. Raghavendra,
Yes.
thank you so much for your inspiring talk and your inspiration to many of our students, also to enter Andhra Pradesh BSc students. You are a role model to many of our scholars also. You have given a wonderful lecture and that really inspires us and motivate us. Thank you so much for sparing your valuable time and your valuable suggestions. Thank you so much. Your support and your encouragement needs our students as well as government of Andhra Pradesh because you are the student and once upon a time you are the student of Andhra Pradesh. So we really need your support and
We are still the
if we find any good student, yes. If we find any good student, we really send to you, and you have to for regarding PhD scholars, you need to support us. Thank you so much for your wonderful lecture. Thank you. Now the next speaker, Dr. Dr.I.VIJAYA Garu, and our my colleague Anuradha Madam will give an introduction about sir.
Am I audible?
Yes, you are. You're audible, ma'am.
Today's webinar, Dr.I.VIJAYA Babu Garu, Principal of Dr. V.S. Krishna Government Degree College, Visakhapatnam, and convener of this webinar, Dr. A.V. Ramesh sir, Head of the Department, Department of Chemistry, and Organizing Secretary, Dr. M. Gopi sir, IPSC Coordinator, Dr. K. Ravi Babu Garu, and all the participants of this webinar. A very good morning, all of you. Myself, I am Dr. C.H.S. Anuradha, lecturer in chemistry, Dr. V.S. Krishna Government Degree College, Visakhapatnam. It's my privilege and indeed an honor to introduce you to you all, Dr. Dr.I.VIJAYA Garu, an eminent personality, eminent invited speaker of today's webinar. Sir currently working as assistant professor in the Department of Chemistry, IIT Kanpur, India. Regarding his educational qualifications, Dr. Dr.I.VIJAYA Garu, he completed his Master of Science from University of Hyderabad and graduation from GDC Chodavaram, Visakhapatnam district, and he completed his PhD from University of Groningen, the Netherlands, on the thesis entitled Analysis, Photochemical, Spectroscopic, and Electrochemical Studies under the supervision of Professor Wesley, Dr. Brown, and Professor Bernard L. Feringa, Nobel Prize winner in Chemistry 2016. And he completed postdoctorate from University of Groningen during April 2014 and June 2015. During June 2015 to November 2018. And regarding technical expertise, expert in building Raman instrumentation, especially Raman transient resonant Raman spectroscopy and surface enhanced Raman spectroscopy (SPRS) of inorganic complexes, DNA, and protein samples. He also has expertise in X-ray absorption spectroscopy (XAS) and also electrochemistry of inorganic metal complexes, cyclic voltammetry, and also spectroelectrochemistry. And Sir got so many awards and grants. He got a grant of SERB CRG grant on metal peroxynitrate synthesis and reactivity of worth 49.72 lakhs. He also had the grant of CSIR grant, structural and functional mimics for class 1C ribonucleotide reductase synthesis and reactivity of worth of 16 lakhs. UK for the year 2012, and he obtained STSM grant of 2015 euros under COSC action to work on iron complexes and as well as nickel complexes. Regarding his SAR published more than 40 research publications in renowned international journals. With this, a very Dr. sir to deliver his talk in this webinar. Thank you for giving me this opportunity.
No. Fine, sir.
Okay, yes. Now it is good. So am I audible?
Yes, you are audible.
Okay, so
Perfect, you are audible.
yeah, thank you very much for this wonderful opportunity. So today I'm not going to talk about more about science. So what Ramesh sir has asked me to talk about the journey that I had through my career. Okay, so if students are comfortable in Telugu, I can try to make it in Telugu, or if you prefer in English, I can also do the same. So what do you prefer?
You can go with whatever comfortable to you, and as well as students. Bilingual is better.
Okay, bilingual is better. Yes, I'll do that. So second. So am I allowed to share?
Yes, you are. Yes, audible.
No. Am I allowed to share? Because I'm. One second. I'm trying to find the file. Okay, so is my slides visible? Yeah.
Now it is sharing. Now it is sharing. Yes.
Yeah. So my slides are visible, right?
Uh,
Okay. So thank you very much for the kind introduction. So this is Appa Rao. So people call me as Appu. So now I'm currently faculty at IIT Kanpur. So this is my journey to this position. So can you recognize this place? Actually, this is Vishakhapatnam. And you go, so I am coming from this Madugula. So Madugula is a very rural village. And I came from very like a below middle class family. Okay. So, and most of my study has been done in my village only. Okay. So from 1st to 7th is a RCM girls high school. So since it is a girls high school, after 7th, they kick you out from the school. So then I need to move to Jilla Parishad school. Okay. That's a government school again. And where I finished 10 to 7. 7 to 10, sorry. So then I moved to college. It's a government junior college. Actually, this is the place where Ramesh sir is also actually worked as a lecturer in that particular college. So during this period, actually, I was good at cricket. The reason is, I was also good at mathematics, but at the stage, the guidance that you get from the people that are around you, they said, okay, so mathematics you may not have future. Okay, so it's better you move to somewhere else. Okay, with the mathematics, all you can do is actually probably you can have a tuition center or become a teacher, not more than that. So that is a wrong impression. But at the age of 12, nobody knows what is right and what is wrong. So then I'm mainly interested in the physics, but the problem is I was really weak because none of the teachers are actually good who is teaching physics in the rural area. So they were not good. So obviously, if the teacher is not good, then it is difficult for you to learn from yourself. Okay, but fortunately, I have a very good chemistry teacher. So Vijay Kumar, his name is Vijay Kumar. He's exceptional in teaching chemistry. So actually, he dragged me to the science. That is chemistry. So then, at this stage, so you see, at the age of I would say 16 to 17, the aim of a student probably at that time I want to become a teacher, a school teacher. Okay, because our thinking process stops there only. So then I moved to for the BSc, I moved to Chodavaram. It's like 20 kilometers away from my village. Okay, so here also Ramesh sir used to teach the chemistry, and he's actually my chemistry teacher during my BSc. Okay, so but financially we are not really strong, family wise. So then what I used to do, like a lot of tuitions at home. Okay, so then immediately after I finish intermediate, I started tutoring intermediate because they need mathematics. I was good at math, so then I did that. So that actually, that's how I manage some money. So in Chodavaram, so the idea is, okay, after BSc, what you want to do? So people may think like you can go to the master's degree, or you can prepare for some competitive exams to get the jobs. Okay, so these are the options. So many people actually go for that. So because majority of the people wanted to do the job after the BSc. Okay, so then there are like some universities, I mean, those entrance tests you can actually go and take. For example, Andhra University, Nagarjuna University, KU, OU. Like this, we know. We don't know much information at that time. You also do not have internet. See, those are the times we don't have internet. It's very difficult. Phones are difficult. Okay, so then, and we hardly know about Hyderabad Central University and IISc. IITs, I don't even know. So somehow Gopi has managed to like get into IIT Kanpur, but it was really tough for any people from rural background to crack that exam and to get into an IIT. Okay, so in that regard, it was really good. So the goal here, see, again, it changed because the way, I mean, where you spend your time, so that changes your goals. Okay, that's why you should be having very, very good friends so that you can move forward in a nicer directions. Okay, so at that stage, so I wanted to do a master's, and in fact, I did write this Andhra University exam, I mean SET exam, and also Hyderabad Central University. I did get the seat in Andhra University. Okay, my rank at that time was 26. Again, people told me that if you do your master's in the organic chemistry, you will get a job for sure. Okay, so like it's probably like a 20,000, 30,000 in a company, you can get a very decent job. But any other chemistry, if you do, again, it will be difficult for you to find a job. And that is also wrong. Okay, that is also wrong. See, again, here people around you will change your way of thinking, your psychology. Okay, it's very important for anybody to have a good friends again. So I joined Andhra University, and at that time my thinking was, okay, so if I get a job in a chemical company with 20,000, I'm happy, or teaching job for that matter. Okay, so I mean, now you can see, so from my village to Andhra University, it's like 80 kilometers. Okay, so I am away 80 kilometers away from my hometown. And let me also tell you, I was really, really bad at organic chemistry. I mean, to be honest, now also I'm really bad, but people information kind of forced me to take the organic chemistry. Okay, so then during that period, so I also told no. So I also gave an exam to the Central University. Okay, Central University is the University of Hyderabad. Okay, and in order to get into that place, it's not only the one. I mean, exam is not only the one. You need to crack the exam. On the top of that, you should go and give interview. Think about it. So Andhra University up to BSc, it's Telugu medium. Okay, so I did not really do much. I don't know how to speak in English. Okay, that is the first barrier. Okay, so how you go and answer the questions. These people will ask a question, everything in English. Okay, it was difficult. Okay, but okay, still somehow I went, I managed, and I got the rank of 17. Okay, then now I got the seat in Hyderabad Central University. Okay, so then see, now I'm away from the home 750 kilometers. So every time it's like 10 times further I'm going. Okay, so but the Central University, when you reach at a university like HCU, again your mindset will change, because people at Central University don't think about jobs anymore. Okay, their psychology is different. Okay, they wanted to explore the research. They wanted to do like bigger things. Okay, they wanted to go abroad. Okay, they wanted to do PhD in abroad. Okay, they go to this Baba Atomic Research Center as a scientist. Okay, where you get a very decent jobs. Okay, so that's why this exposure is very important for the student. Okay, you need to know what are the possibilities that you have to explore. Then only you can actually, so you will have a chance to go further and further. Yeah. So here again, my aim changed. I came to Hyderabad Central University. See, from Andhra University, I spent only 2 weeks. Then I moved to Central University for the masters. Then Andhra University, I wanted to get a job in the industry, like for 20,000. Then I moved to like Hyderabad Central University. Then that is my previous goal is not there anymore. Now I want to do the research. Why? Because here the teachers and the professors that you have there, that is what they teach. Okay, so the teaching is so good, and actually students will motivated to go towards the the PhD side to perform a research side. Okay, and for your information, so in order to get a PhD in any institutes in India, okay, there are 2 exams that you need to clear, or one is good enough. One is a CSIR net, another one is GATE. Okay, if the teaching is really good, the level of teaching and your understanding is good, then you should be able to crack during your masters only of first year. I did that. During the first semester of my masters from ICU, I already cleared Sciences-2022. Okay, so again, the teaching, that is very important. Okay, so if you don't practice well, then it will be difficult for you. Okay, so pay attention and have good friends, then that will actually motivate you towards like a different heights. Yeah. So, but now also there are so much information available in the online. So please make use of that. So again, after I finished my masters, I got admission into several IITs and IASC and HCU. Because see, I had a CS at that, I had CSR or GATE. So then it is not a big deal. Okay, you get it. So like that. So then here the another possibility, which I think is a little bit lacking in the university stage, is the exposure to apply abroad. Okay, so bigger institutes like IITs. So now so many of my students who are doing masters in our lab, okay, this is in our lab. So many of them actually went abroad, either States or Europe. Okay, so that exposure is little bit lacking in the university side, but so you can always reach out the people and get this information from. Okay, so then that will be helpful for all of you. Okay, so at that time, actually, I had a good friend, and I came to know that there is a PhD position available in Professor Wesley Brown lab. Okay, Professor Brown and also Professor Ben Feringa. Okay, so these two jointly has a PhD position available. Then I applied. Again, remember that PhD boss with the Brown is actually an Irish guy. Irish people, how they speak English. Okay, it's like a British English. So it's so difficult to understand. So it took me almost like 2 years to understand 50% of what he's talking. Now also I have difficult time. Probably I will get only like 80% of what he's talking. But see, life always give you challenges. You just need to like face them. Okay. So in that case, I had a 4 interview, and I hardly understand what he said. Then whatever the keywords what he spoke, based on the keywords, I was able to like address. Whether I addressed well or not, I don't know. It is up to him. But I addressed his concerns based on the keywords that I heard from him. Okay, so but nowadays I think you may not be in that situation. Okay, so please learn English. You have so many options. Okay, learn better, so then you will be in a better position compared to me. Okay, so like that I got to know about that that information. So now I got the PhD position in University of Groningen. Okay, it's in Netherlands. Okay, Netherlands, the PhD is 4 years. Now you see, now I am traveling from Visakhapatnam to Netherlands, that is almost like 7,500. It's again 10 times distance. Okay, so again far from home, but it is okay. See, if you go different places, then only you can learn the culture of that particular place. Okay, so it is better to explore that also. Okay, so you never know what new things that you can learn. Okay, so these are the two gentlemen. So one is Wesley, and here professors, we never call them professors. They will get offended. Okay, so any abroad, you call your faculty and they with their names. Okay, this is another. See, we are from India. We have a lot of respect to the respect to the faculty. I hope that is true. And they said, okay. So initially, I used to call Wesley, yeah, sir. Then one day he said, my name is not sir. My name is Wes. You call me Wes. Okay. So then that is the culture. See, when you and your boss are equal, then whatever the science that you develop, you are not in fear anymore. Okay, so you are free to explore, and if you don't agree with your boss, you can disagree. Okay, that is wrong. Okay, this is what I think is correct, and you have that freedom, and that is something you can get in abroad. That is something you may not find in India, because in India we respect faculty, but sometimes it's too much. Then the respect should not be a fear. See, faculty is there, your teachers are there to teach you. If you're not approaching them to learn something, then what is the point? If you have doubts, you better go and ask. Okay, if you don't ask, how do they know? Okay, if you have a lot of fear, then you will not learn anything. Okay, so make sure there is nothing wrong. Go and ask. Okay, so they believe me, they will clear your doubts. Okay, so you don't need to worry about it. Yeah, that is what I wanted to tell you. So here also, we are very easy to access. So several students will come and discuss with us, and we discuss with them, we never say no. Okay, so this is what I'm saying. So if you go and, experience the other cultures as well, and it is also good for you. Yeah. And in a previous lecture, Raghav mentioned, right? Raghav was talking about Feringa only. Ben Feringa. He's the one who got Nobel Prize in 2016, and actually he's my PhD supervisor. One of the PhD supervisor. My main supervisor is Wesley Kahn. Okay, and good. I have learned so many things in Netherlands. Okay, unfortunately not Dutch, because I know I will come back, so there is no point to learn Dutch. But anyway, so the culture I learned, the science is really exciting. And he's an expert in electrochemistry, photochemistry, and Raman spectroscopy. And I learned all of those things from Wesley. Okay, so this is the benefit. If your boss treat you like equal, you can actually go and learn. Okay, so that is very good. So then from here, okay, I'm already kind of mature. At this stage, 2013, I already defended my PhD thesis. Very good. And now it is my next step. I need to go to explore even more research. Okay, so for that I need a postdoc. Okay, so PhD, you work under somebody. You are dependent. When you do PhD, people think you are dependent because the projects and the research, everything that you develop is actually supervised by your boss. In my case, these two. Okay, but when you go for a postdoc, then a postdoc means what? After doctorate. So once you get the doctorate, that means you're already expert in a particular field. You're getting doctorate degree. No, once you get a doctorate degree, it has to have some meaning. That means you are good at doing something. Okay, and if that means you should be also good in supervising somebody else in that particular field. Okay, postdoctoral experiences for that. Okay, it will teach you how to become a supervisor, how to become a mentor for other students. Okay, so your faculty is doing to you, so that is what it's mentoring. Okay, so tell how to do science in this case. So then for that, I moved now 13,000 kilometers to USA. Okay, it's called University of Minnesota. It's at the border of Canada, really cold. It can go to minus 50 degrees centigrade in the winter. If you go outside, you freeze. If you what is that? Cry, the ice will become what is that? The tears will become ice. That much cold. Okay, but it's okay. Again, this is the experience. No, so that kind of experience you cannot get in sitting in Vizag. So in Vizag, do you get snow? No. So what is the lowest temperature that you can reach? Probably like 12, something like that, 10, not more than that. So minus 50, if you put water, it will freeze there. You don't need fridge. Okay, so so this is Larry K. And Larry K is the pioneer. Okay, he's the expert in the field. Okay, see, this is also important. If you go to the experts, they will teach, they will give you their experience. Science is something you can learn from anywhere. Even if you read the papers, you can get. But this experience, you can only get from experienced people. Okay, so the mentoring is something you will learn very well from an old professor. You can see how old is he? He's turning 70 next year. Okay, exceptional guy, exceptional. Okay, so great understanding of inorganic chemistry. Okay, he's my mentor. Okay, so during his time, I mean, in his lab, so he gave full freedom. I can do whatever the hell I want, and I did. Okay, so we did some amazing chemistry, and there are several publications also came out. And as I said, I also supervised several students from his group, and I also learned the mentorship. Okay, now you see, from at the 12th standard stage, I wanted to become a school teacher. That changed to like go to the industry and earn some money. Then do a PhD student, research scholar. Then postdoc. Now I'm become a scientist. Then what? After becoming this level, you have a knowledge. What do you want to do? Then either at this stage, you can either go to the industry. With the experience that we have, experience that we gain, we get a lot of money. Simple. But or if you really have passion for the science, you go to the academics. These two are two different things. So if you go to the industry, you may not have freedom that you wanted to do. Let's say I want to explore the science, understand the science. You may not have that in the industry, because industry already has problems that you need to solve. But academics, you are free to explore anything. Okay, so it is a choice. Industry, you get a lot of money, and academics, you'll get only this much money. Okay, so again, if you have passion, go for the science. You know, I already have enough passion. Now I need to earn money. Go for the industries. Okay, both are science only. Okay, it's your choice. What do you want at the end? Okay, so the point I wanted to make here is the surroundings actually changes a lot. They influence us. Okay, if you get influenced at the early stage, you may not achieve greater heights. Okay, so you should be like broad-minded. Okay, open your mind and try to explore things. See, do not satisfy already. Okay, you're not old, you're very, very young. Yeah, so please think about that. So from here, so then recently we published an article. Okay, so that is published. I don't know whether name is irrelevant to you because you may not know. Okay, so here they took my interviews. There are set of questions that they will ask, and you need to give your opinion on that. See, here the first thing I already mentioned. I chose chemistry as a career because I told you I was poor in physics, but I liked physics a lot. But biology also I'm really scared. But chemical colors actually fascinated me. So chemistry is something that I get a lot of. I mean, I have a lot of passion. So that's why I moved to the chemistry. Okay. So if anybody interested, you can go and read. It's okay. Then when I finish with my postdoc at Larry's lab, then it is time for us to find the real job. Okay. In other words, is a permanent job. Okay. So then there is again a lot of struggle. It's not that you apply, you get the job. It's never easy because India population is 130 crores. There's so many people who wants to get the job, not only you. So that means you should be good. Then only you will be selected. If you are not good, you will not be selected, and you should not be disappointed for that. Okay, so you should know exactly how capable you are. Okay, so you should know, and if you think you're not capable, okay, work on it, and that is very important. Okay, if your goal is really high, you should also work hard. If your goal is very less, it's okay, you do that work only, and you gain that much only. Okay, and it is very important in that regard. Yeah. So then I again I apply for the jobs in here one more thing I wanted to tell. Actually, with the experience that I have, if I go to the industry, I will get job very easily, and because I am expert in a particular things, for example, Raman spectroscopy, which is very hot in the industry. If I apply, I'll get a very, very good salary, no doubt about it. Okay, but somehow I wanted to come back to India and work in the academics. So that is actually from the beginning only, that is what I'm thinking. And lucky for me, when I applied, I also got the opportunities to do that. Okay, I applied multiple places. IIT Kanpur is the first one to offer. Okay, and after that I got several 2 more offers, but I declined because I already at the IIT Kanpur, and IIT Kanpur is the best. Okay, so Raghav said no, so IIT Kanpur is the one of the oldest IIT oldest IIT. Okay, so a lot of people here actually do very, very good science. Yeah. So this is about me. So I told that story because, I mean, to be honest, Ramesh sir asked me, because talking to this story, I never really did. To be honest, giving a scientific talk for me is a lot more easy. So talking about my personal experience is actually not my cup of tea, but it's okay. So now I'm going to go through few slides. So then how and what are the opportunities or possibilities that you have as you are a graduate student or with a BSc or MSc, and what are your options at your stage? Okay, so as you know, if you want to do the master's degree from after the BSc, okay, so you have several options to join in IITs or IISers. IISc, you know, there is one, IISc Bangalore, and you also have NITs, National Institutes. Okay, all these institutes, you can get into the admission through JAM, Joint Entrance Exam. Admission to master's degree. Okay, and if you get a good rank, and you can, you know, choose, there are 23 IITs and 7 IISers and 1 IISc and 31 NITs. See, you have so many seats available. You have so many. If you crack that exam, you can be in a very, very good institute. Believe me, these institutes are really, really good, and they will give you a very good opportunity to explore further. Okay, but on the top of that, not only JAM, but several institutes. For example, see, in this list, there is no Hyderabad Central University. Central universities are not there, and locally, state universities are not there. Okay, those will come under this category. Okay, so these institutes actually, they conduct their own exam, like ASET, AU set, okay, KU set, OU set. So like that, if you crack those exams and you can get admission into them, then you perform you conduct your master's degree, and from there you explore further. And see, at the beginning, when I was a PhD, when I was a master student, and Gopi is also actually my senior, and at that time we had only 5 IITs. Now look at the number; it's almost like 6 times. 5 times it's increased. Okay, so you have more opportunities now. Getting a position into these IITs now is relatively easier than 15 years back. Okay, you have a lot of opportunities now. So what are the perks that you get if you study in any of these institutes? First of all, the teachers that you are having, they have exceptional teaching skills, because they take teaching very seriously, and the level of teaching, the material they cover is so deep and so high level, so then you will actually motivate to do the research, to do some science. Okay, and on the top of that, it's not only the bookish knowledge that you need, you also need to know how to work in the lab. Okay, and those facilities are also here. These institutes are really good because they are, rich institutes, I would say, compared to the state universities. Okay, they maintain the lab facilities for chemicals. Okay, that is why you may need to aim for them. Okay, and the other thing is, when there is a semester break, you have a possibility of explore internships. There are so many internship possibilities. Every institute has its own possibility for the master students, like some students to they can go and they work in their universities or institutes. Okay, that will give you exposure like 2 months or 3 months. You can do that. Okay, since the training is so good, then obviously, see, if the training is good, you will be good. You will be knowledgeable. If you're knowledgeable, obviously, then you are in the job market. It's easy for you to get the job. Okay, and more importantly, I don't want to emphasize this, but brand name helps. See, everybody says, yeah, I am from IIT, I am from IISc. Yeah, actually, sometimes it works. Not sometimes, majority of the times. Okay, and more importantly, in these institutes, they will give you stipend also if you are academically weak sectors. Okay, if you show the certificate that my family is not earning more than 6 lakhs per annum, okay, you can actually avail those fellowships, okay, to conduct your masters in those institutes. Okay, since these institutes are actually well versed with in connection with the abroad universities, okay, abroad institutes, then that will also help you to, next one, your next goal, journey could also be abroad, not necessarily like within another institute in the India. See, India, how things work, you already know. It is also a good idea to go and explore and come back. Okay, so learning new things is always useful. Okay, so this is for the master students, BSc students, how to enter into the masters, and this is for the master students, how to enter into the PhDs. Okay, so there are 2 exams in India. They conduct. One is a CSIR. Okay, CSIR you need to clear with the JRF. Okay, if you clear with JRF, you are actually entitled to join any institute in India, because the CSIR, actually the funding body will give you the money, a stipend of 31,000 per month you will get from this fellowship for first 2 years, but the next last 3 years you will get 35,000. Okay, for your information, PhD in India is actually 5 years. Okay, if CSIR is not an option, or probably you are somehow not able to crack that, then you also have this GATE. Okay, and from the GATE, if you actually get the score of greater than 500, you will be called for the interview. Okay, that is the cutoff for IITs and all. Okay, so you make sure that you get good score in the GATE, and on the top of that, if you actually get 90%, greater than 90%, then you can also get a PhD position in Singapore. For example, the previous speaker Raghav was actually GATE topper. During my time, he was the topper of in that GATE exam, and he got the admission into National University of Singapore, NUS. Okay, so that means those options are also available to you. Okay, so the other one is actually, there are other institutes, they also conduct their own exams. Okay, IISc Bangalore is one of them, PARC is one of them, and ISRO. But these are all possibilities that one can explore. Okay, again, the perks that you get if you join as a PhD student. Okay, so again, your supervisor, he or she will be having very good experience, so then they will teach you how to do the science. Lab facilities will be good. This one I already mentioned. So if you are a CSIR fellow, you will get 31,000 as a salary. Okay, so as a fellowship, salary is because you're not doing work, so you call this as a fellowship to survive, and 35,000 after 2 years. And there is Raghav also actually emphasized this. There's a PMR fellowship. Okay, this is a very prestigious one. If you get that, you on average you can get 75,000. That is higher than the salary of the postdoc. Okay, so that is something to watch for, because if you get that, it's very prestigious. Okay, again, if you're good at doing the things that you're doing, then your job hunt will be easier. Once you finish the PhD, you can go and explore the postdoc opportunities. Yeah. So the other ones are actually USA, Canada. If you wanted to go, you need to clear 2 exams. One is TOEFL, another one is GRE. What I heard from my students, that probably they are scrapping the GRE. They are only going based on the TOEFL, so that you look for that. And this is for the USA and Canada. But if you wanted to go to Australia and other European countries, what you have is IELTS. And this exam is relatively easier than TOEFL. Okay, so if your target is these countries like Europe and Australia, go for this. If your target is to go to USA or Canada, then TOEFL is the one that you need to crack. And Germany, there are some fellowships that are available. Okay, for example, that fellowship and Humboldt fellowship. Okay, these fellowships will put you in Germany, and you can also do PhD there. And as I said, if your GATE qualification with greater than 90%, and you can go and work in Singapore as a PhD student. Okay, so sometimes in some cases industry fellowships are also available, so you can also avail them and look after them. So obviously, so if you are good and after you get your PhD in a particular research, you will be already expert in particular fields. You can be inorganic chemist, or you can be organic chemist, or you can be like a material chemist or computational. Okay, depending on your expertise, you can go into different fields. Academic researcher, like a faculty, you can go. Okay, and if you are learning techniques during your PhD time, then you can go as an analytical chemist or biotechnologist. Okay, and again, since obviously you're doing chemistry, then chemical engineering is an option for you. And in the chemistry, many of the people actually also explore the biology. Okay, that means they can also explore the biochemistry options. Okay, so then forensic is one thing that is more mainly come from the analysis. Okay, then a lot of spectroscopy is needed. And you can also work in the scientific laboratories as a technician. And there's several industry jobs. There's so many companies will take you. Okay, if you do a PhD in chemistry. Okay, these companies can be in India or abroad. The one thing that I wanted to emphasize, and I'll leave the thing here, the opportunities are plenty. We have a lot of opportunities. We should be ready to grasp them. Okay, so if you're ready to take them, then you will get it. If you're not interested in take that opportunities, then you'll never get them. Okay, so the information is very important. Okay, these are the things that are already available. If you know about them, it's a lot more easy. If you don't know about them, then it is difficult. Okay, so then higher studies will place you in a better position. If I stop at 12th standard, then probably I will be like a conductor. If I stop at degree, probably now I will end up in a company. So if I stop at PhD, I'll be a teacher. If I stop, after postdoc, see, now I'm become a faculty. So higher the education, higher the quality that you acquire, and better your position will be. Okay, so see, without pain, there is no gain. As simple as that. Okay, so with this, actually, I gave the background about my journey and also what are the possibilities that you have as a chemistry student. Okay, if you allow me, since I'm a faculty, I like to discuss science. Okay, so shall I go with this? Shall I go ahead with the science, or do you have any questions so far? Gopi, shall I go with the science or? Hello? Is anybody there?
Apparao.
Yes.
Yes, you can continue.
Okay.
Yes, you can continue.
Yeah, I think that topic is completely different. So now I'm going to talk about the science. Is it something, people want to, any question section? No, right?
Okay. Briefly, you can complete about your research work and such ideas.
No, this one is actually like I'll take only 5 minutes. Because I don't want to bore you more. Okay, so actually by training I'm an organic chemist, and I have expertise in multiple spectroscopic fields. Okay, and I use the spectroscopic tools to understand the complex reaction mechanisms. Okay, that's why the shedding light on a biomimetic inorganic complexes, and I use a multi-technique approach for that. And you know, the grand challenge now is we are out of fuels. Okay, and majority of our fuel source is the petrol, and we all know petrol is actually, you know, it's non-renewable. You cannot get it back. Once you use it, it's done. Okay, and moreover, when you use it, you emit carbon dioxide, and the carbon dioxide is the one which contribute to the global warming, and that's also something that we need to watch for. And sadly, there is a lot of natural gases sources are available. It's not that we don't have them. We do have them, but we don't know how to use them. So instead of using them, we actually, burn them. Okay, without even using, so we are actually flaring a lot of natural gas. The main component of natural gas is methane. So why don't we use it? The problem is handling of methane or handling of any gas for that matter is very difficult. Okay, so that's why if you find a way to convert that methane into something else that you can actually store. Okay, so that means methane, if you actually oxidize it, and what you form is methanol. And by the way, oxidation of methane is not an easy task. It's a very, very difficult task. Okay, let's say, imagine that you have done that. If you've done that, then now methanol is a solvent, and you can actually use that as a chemical feedstock or fuel for the vehicle, or it can be easily stored or easily transported. Okay, so this is our challenge at this stage. So then how do we solve it? To be honest, we don't need to solve, because nature already has given us a way to handle this. In the nature, there is an enzyme. Okay, that enzyme name is methane monooxygenase. As the name suggests, it takes methane and it puts one oxygen. That's why monooxygenase. It puts one oxygen in the methane. Then what you get is methanol. Okay, it's a very, as I said, it's a very difficult reaction, but it can, this SMMO, the enzyme can do very efficiently by using oxygen, atmospheric oxygen. And if you look at the actual guy who is doing this job in this structure is the di-iron 4. Okay, it's a diamond core species that is actually responsible for the conversion of this methane to methanol. Let's see if we actually understand how these things work, or if we actually develop a catalyst that can actually mimic this structure and do something and do the same thing for you, then that is very good, because that is what you want to solve our energy problems. Okay, this is called biomimetic chemistry. Okay, so we are learning from nature, and we try to understand that system, and we try to make something similar so that we can benefit from it. Then there is this photosystem too. We know all the atmospheric oxygen that we get in the atmosphere, that is from this reaction. Okay, it takes oxygen, it takes sunlight. Okay, and it converts your water into dioxygen. Again, if you take this reaction, there are 4 electrons and 4 protons are needed to convert water into oxygen. It's a very, very thermodynamically uphill process. It is difficult to achieve, but this photosystem too, where you have manganese oxo or calcium, this guy can do this job very efficiently. Okay, so that means understanding these systems or developing synthetic models for those systems will be beneficial. We also work along on the same lines, okay, but not necessarily on the previous 2 enzymes, but what we work on is a bleomycin, okay, enzyme called bleomycin. So the bleomycin is the one actually works as an anti-cancer agent. Okay, so we have it in our body, the bleomycin. If you have any cancer, and this is the guy which fight for you. So here is the coordination. The inorganic chemistry part of it is something that we are interested in. You see here, there are 5 nitrogens that are binding to iron, and this reacts with the dioxygen, and that gives you a species like this, a iron 3 OOH. Remember, this OOH is H2O2, hydrogen peroxide. The hydrogen peroxide go and binds with the iron 3. And this is the one which is responsible for DNA cleavage. If you cleave the DNA, then you kill the cell. If you kill the cell, there is no cancer. That's how it works as an anti-cancer agent. Okay, and inspired by this system, see, we have 5 nitrogens, and we also develop a ligand that contains 5 nitrogens, and that binds with the iron. And you need to have one open coordination site, because that is where your oxygen will bind. Okay, so that means this place should be labile, and that should be easily reactable with your oxidant. In this case, we used hydrogen peroxide, and when you react this with hydrogen peroxide, you do form this iron 3 OOH. That is same as your activated bleomycin. So that means, in principle, this compound can also probably behave like this enzymatic system. In fact, it does it. It can cleave the DNA oxidatively, and it kills the cancer, but it is not as efficient as the biological system. Okay, so it is so difficult for us to completely mimic the biological system. Okay, that is our goal as a bio-inorganic chemist. Okay, since this compound is already generating this iron 3 OOH spaces, then we thought, why don't we go one step further? Okay, so here, I mean, if you're interested in electron movements, okay, so that is something you need to pay attention here. So this iron 3 oxidation state and OOH, the hydroperoxide is the one which is attached to the metal. If you break this guy, then what you form is a terminal metal oxide. See here, now you have a double bonded oxygen, and it is so reactive. It is very reactive, and it can oxidizes your substrates. Okay, and many biological systems in our body rely on this guy. This is called compound 1. I did not put the details because I don't want to confuse you. So, but this compound reacts with the halide, and it generates this iron 3 OX. This is called haloperoxo intermediate. Okay, so this is the intermediate that you get in haloperoxidases. These are the enzymes that are responsible to put halides in your molecules, because several of our drugs that we take, they have halogens. You see here, fluoro, fluoro, chloro, and here you have fluoro, chloro, and like that. You have in some cases you have bromo, some cases you have iodo also. Okay, that means the halogenated products are very, very important for us. Okay, and these are the enzymes that are responsible to incorporate those halogens into those molecules. So the understanding is, okay, now our compound can do this. Can this guy do also this? Can this form this iron 3 OCl? Okay, a simple question arises. Then what we did, you take our model compound, and all you need to is, see, you need OCl binding. All you need is sodium hypochlorite. It's a bleaching powder that we put in water to kill the germs and all. Okay, so bleaching powder we call it. And if you add that, then what you get, you are getting a banded 480. Okay, by the way, this is called absorption, UV absorption spectrum. Upon addition of sodium hypochlorite, that is the bleach, and your band is dying, that means the initial compound is converting into something else. That something else has an absorption band at 480. And now we need to know, what is that? Is it this guy? How do we know? So we have to do some kind of spectroscopy to understand that. So in that case, we did EPR spectroscopy. EPR is electron paramagnetic resonance. Okay, if you have any unpaired electrons in the system, that can be detected by the EPR spectroscopy. And in fact, we did that, and we got signal. Here you get a derivative shaped peak. Okay, and this signal is actually indication for an S equal to 1/2. That means you have one unpaired electron in your system. This is what it's telling you. So you have learned crystal field energy, CFT, crystal field theory. If you learn crystal field theory and you immediately realize if you have an iron 3 that is in the low spin configuration, you will have 1 unpaired electron. If you have 1 unpaired electron, that can be seen by EPR, and you get the signal at G around 2. Because again, if you learn EPR spectroscopy, the Landé factor, that GE is around 2. One unpaired electron give you signal here. That is what it tells you. The other thing that you can actually use is the mass spectrometry. Okay, so here in the mass spectrometry, so I think you, if you are studying masters, I think you will know this. Okay, so it will give you the molecular formula. Okay, when you put your sample in the mass spectrometer and you get signals like this. Okay, and this signal is the exact mass by Z ratio. And based on this signal, you should be able to tell what is the composition of your molecule. In this case, this signal tells me that I have my ligand, 1 iron molecule, 1 OCl molecule, 1 perchlorate molecule. Okay, and based on this, I should be able to tell the oxidation state as well. OCl is a negative, ClO4 minus is a negative, my ligand is a neutral. That means total charge is positive. That means my iron is an iron 3 oxidation state. That is what my EPR is also telling. Okay, EPR and the what is that? Mass spec is telling me the same thing. Okay, so then, as I said, I have some expertise in the Raman spectroscopy, and I used Raman spectroscopy to know whether the OCl is binding or not. Okay, if you have an OCl like this, you see Raman spectroscopy is nothing but this vibration, IR spectroscopy. Okay, it gives you the vibration information. If I have iron OCl, that means iron and OCl, iron and oxygen, that can vibrate. OCl, that can vibrate. The vibration of OCl bond and vibration of iron oxygen, they need different energies. Okay, so that means they appear at different frequencies. Okay, some signal, some are coming here, some are coming here. Okay, so again, the vibration is actually depending on the mass of the atom. This is coming from your Hooke's law. When the atom gets heavier, then so the frequency also lowered, because Hooke's law is actually root K by mu, right? Force constant over reduced mass. If you increase the reduced mass, your frequency will be lowered. That is what is happening here. See, for example, this 580 peak, when I labeled oxygen with O18 isotope, then that peak is shifting. This is called isotopic labeling. Okay, so that is clearly telling me that when I labeled oxygen, my vibration frequency is actually shifting. So that means it is actually OCl vibration. Okay, so like that, we characterized for the first time this iron OCl, and which is the functional model for haloperoxidases. Okay, so later we discovered several, and here one more example with the ruthenium OCl. Okay, we take ruthenium compound, upon addition of OCl, we got the same. Okay, OCl bound ruthenium compound, and in this case, this compound is actually reactive. Reactive means, since it is an oxidant, it should do some oxidation reactions. We added some phenols, and phenols get oxidized and give you the corresponding radicals. Okay, so here in the first slide, I talked about the, so to solve our energy crisis, and we developed a metal compound that is based on the ruthenium. Upon reaction with ceric ammonium I would like to show this video. See, this is the ruthenium compound. When we add the ceric ammonium now you see there are so many bubbles. So these bubbles are actually oxygen bubbles. Okay, so that means the catalyst is able to oxidize water to dioxygen. Okay, so this is the one that we need to know, because in the starting slide, I told you in the photosystem 2, okay, that manganese compound can do the job. Now here we are doing that with ruthenium. Okay, so see, there are so many bubbles. So these are actually coming from the oxygen, from water oxidation. Okay, so my group actually works on multiple things. So And this is some example: bioinorganic chemistry, mechanistic aspects, electrocatalysis, and photochemistry. And this is my present group. And thank you all for the opportunity. Thank you very much. Gopi, I'm done.
Parov,
Yes, yeah.
over. Thank you so much, Dr. Parov from IIT Kanpur. You have given us a wonderful lecture. It's really inspire our students from Module to Hyderabad Central University to Netherlands to USA, and again come back to India in a reputed institute like IIT Kanpur. I studied there in IIT Kanpur, but I did not get a position, means we could not achieve. But you are inspiration to many of our students who have a better middle class family background, and you are the one you are the one example for the students like from our government degree colleges. You are from government degree college Chodvaram. We are so proud of you. You are from our area and also from Andhra Pradesh. So your support and your motivation always required to our degree students. And if any chance is there, we will send you our students, PG and UG students. Please motivate us and please make them like you, not like us. Like you, and not like us means, see, the goal should be high. Then only we can reach the positions like you. And you have given a wonderful inspirational talk about your career and your journey from Modular to IIT Kanpur. It's really inspired us. Thank you so much for sparing your valuable time with us and to our students. Our students are really inspired and they are blessed with their blessings. Thank you so much once again. Now we will move to move to next session. Ram, you can join. Okay. Zoom lo join అయిపోయా. Okay, ఉన్నావా? జాయిన్ అయ్యావా? నీది అన్మ్యూట్ చేస్తాను. మేడం అన్మ్యూట్ అయిందా? అన్మ్యూట్ చేయాలి. రావి అనా host. Ramu, now you are host. Okay, you can. అట్లనా ఒక ఫార్వర్డ్ ఇచ్చాను నెక్స్ట్ ఎస్ సార్ అన్నిట్లో రాము అక్కడ క్లిక్ చేయట్లేదు చేసాము హోస్ట్ చేసాను
இந்த போஸ்ட் ஒரு 5 மணிக்கு அவர் கன்வென்ஷன் பரவாயில்ல ஆயிடுச்சு హలో ఇది పోస్ట్ నీ పోస్ట్ ఇచ్చావు ఇందాక ఓకే ఓకే what did Romney unmute host లో ఆయన చేస్తున్నారా మేడం ఎవరు సార్ ఎవరిదండి ఫస్ట్ ప్లేస్ మ్యూట్ అవ్వట్లేదు మేడం ఎవరు హోస్ట్ చేసి మరి అమౌంట్ అవట్లేదు
Hello. Hi. I think it is audible now. Hello. 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 Gopi.